Okay. So yesterday we looked at the gold foil experiment, and it was super important because that's the first time that anybody had realized, okay, there's a solid, dense, inner portion of the atom. Up until then, they had thought, hey, there's maybe this plum pudding idea where there's a positive component, but we don't really know like where the positive is. It's just kind of in there somewhere, right? And so having the gold foil helped us to realize a couple really important things. Is 19 the way we're at?
Yeah.
Okay, so we watched the video, but we went over the slide, but here's the, for you to fill in into your notes. So again, Ernest Rutherford was a student of J.J. Thomson, so he was involved in that whole plum pudding business, and he's the one that set up the gold foil experiment. And so those positive alpha particles went through and all the way through that gold for the most part. But then there were just those few random particles that just like repelled and went all over, kind of, unexpectedly landing in other spots along that fluorescent screen. And because of that, they realized they couldn't just ignore those results. They had to realize, okay, even though most of them went through, which would kind of clarify that, yeah, there is all that open space in an atom, something was blocking some of them and causing them to kind of ricochet around, right? And what they discovered, obviously, was the nucleus, is what they ended up naming it. And that was solid. And it also had to be positively charged. They knew it was positively charged because we know that opposite charges will repel. And so if the alpha particles going through are positive and they hit something that was negative, they would have just stuck to it. But that's not what happened. They reflected or deflected or repelled away from that area. And so they were like, whoa, if positive hits another positive, that would cause what they saw. And so they correctly figured out it's a solid center and you have a positive component to that. Okay. So when those few particles were deflected at those weird angles, it gave them the opportunity to come up with two very important explanations or discoveries, I guess. Okay. And so we watched the videos yesterday, and so from this, it clarified that the atom is mostly empty space. Yeah, and I believe this should be the top of page 2, probably.
Oh, yeah.
Oh, yeah. Thank you, Dane. Yes.
What was the last one on number 9?
And thank you.
Angle.
Angle?
No, deflected.
Deflected?
Deflected.
Oh, my bad. That's on me.
Deflected.
Oh, dang it. Thanks, Kenna. You're welcome.
And thank you, again, always if you need something to like me to slow down or back up, make sure you do that, so I appreciate that. Okay, so it learned that the atom is empty space, mostly. The nucleus is very densely packed. And it is also positively charged. So, yesterday, we talked about a few things. Where are you going to find the majority of the mass in an atom? Don't shout it out. If you know or think you know, raise your hand. Where are you going to find the majority of the mass in that entire atom? What do you think, Brookston?
Nucleus.
Very good, the nucleus. What two things or subatomic particles are in that nucleus? Give me one. There's a proton and the neutron. Very good. So protons and neutrons make up the nucleus. That is what is mostly mass. Where do you find the electrons? Where are those going to be?
Orbiting the nucleus.
Very good. Orbiting the nucleus. So, yeah, I think that's pretty good for a quick recap on maybe some somewhat newish information. So we're going to look at these electrons. This is the final scientist that contributed. His name is Niels Bohr. Again, right around the time that Ernest Rutherford was figuring out the whole nucleus and proton business, Niels Bohr was focusing on the electrons. So he hypothesized that electrons travel in orbits or energy levels. Sometimes you hear them called shells, sometimes you hear them called layers. It all means the same thing, all right? It's these areas. To me, it always kind of looks like a bullseye, where the nucleus is the bullseye, and then like the rings are kind of like on a dartboard or something like that, or a target, okay? And so he's saying that you have these different regions where you have a certain amount of electrons here, and then you have a certain amount here, and then a certain amount here. Notice how they say first shell, second shell, third shell. When you get into chemistry, that's going to be important to kind of distinguish between like what's found where. The only thing we really need to know is like the total number of electrons, so we can compare that to the total number of protons to see if the atom itself is charged, like if it has an unequal number of protons and electrons. The other thing we'll look at are the electrons in the very outer level, which we call the valence level, and that is one of your vocab terms, and it's going to be something that's super important for the next 2 units after this as well. So those outer electrons, what we call the valence electrons, and then the total number. And I'll be very clear when I'm talking, like, am I talking total electrons or am I just talking valence electrons? But as you get into, and Niels Bohr was super important, you'll learn more about him when you get into chemistry, and the differences in those layers and things like that. But for us, outer electrons and total is what we're really going to focus on. And that's one thing that's nice, like physical science is an introduction to physics, to chemistry. It's an introduction to a lot of other areas of science that you'll probably take later on as you get into being a junior and senior. And so we don't get too in-depth with anything, but we get a kind of broad introduction to a lot of things, right? And so it leads us to our final idea, and this is called the electron cloud model. And we realize now that the electrons are not like where it's like on a track where you have to stay in your lane, right? So that's kind of what Niels Bohr looked like, right? It's almost like a track, right? You're in the inside lane, middle lane, outside lane. We realize now, and that makes it good when we're dealing with models and like trying to logistically understand it. But in real life, our understanding of the atom is more kind of like a cloud or kind of a region where the electrons are, and not like I have to stay perfectly in my lane. All right, so he kind of had it simplistic. We think now that it's more like this, okay? To me, it kind of reminds me like of bees buzzing around a hive, like the electrons moving so much like that. And again, that movement of those electrons kind of makes the atom seem solid. And if you think back to that Bill Nye, when you had the 3 fan blades, you know, you could put your finger through when the blade or the fan blades aren't moving. As soon as you kick that fan on, it went and it seemed like it was a solid. Like when he was trying to put that paper through, like it wasn't going through. So the electrons will act that way, right? So again, the atom is not solid. It's more the electrons are moving so much that it makes it kind of seem like that solid. And again, they're not like totally restricted or maintaining one lane or one level or one shell. They're kind of more like in a region, I guess. Is that your back? Holy moly. All right, and so these regions that we now kind of call clouds. But again, for using and working with like atoms, we still use Niels Bohr, his levels and layers, just because it makes it easier to actually understand than like looking at a cloud kind of model. We will come back. We have a song. We'll come back at the end. Okay, we are going to start kind of breaking down the periodic table. The first thing we need to do is we need to look at the little squares. Each element has its own little square or tile on the periodic table. All right, there's about 94 naturally found elements in our world, and then we have about 20 more that we have synthetically created or made in the lab. Okay, and so there's 94 naturally occurring. And so we're going to look at the different characteristics of, or what kind of information is shown on each of these little tiles, and what it means and like how it can be useful to us. So the atomic number, and this is one of your vocab terms, it identifies the element. It's kind of like the fingerprint, okay? So we all have a unique fingerprint, right? That's how we can be identified. And so the number of protons is the fingerprint for each one of our elements. Okay, so all atoms of the same element have the same atomic number. So every hydrogen has 1 proton. Every helium has 2 protons. And so if you know the number of protons, then you know what atom or what element you're dealing with. It's also called the atomic number. So really the atomic number and the number of protons is the same number. Right? So atomic number is equal to protons. It's the fingerprint. It's the thing that identifies the element. So in a neutral atom, the number of protons is going to have to be equal to the number of electrons. So if I have 2 protons for helium and it's neutral, then by default I have 2 electrons too. Oh, maybe I should say also. 2 electrons also. So on this periodic table, I need to grab mine too. The atomic number is the small number, and it's the one that is on top of the little element symbol. Right? And so that is not always the case. Sometimes the bigger number is on top, and so we have to find a way. We'll have to find a way, because there's always going to be at least these 2 numbers on each little square or tile. And so we have to find a way to keep the 2 numbers straight, because the atomic mass, that if you think that this is the atomic number, you think this is the element that has 4 protons, and I believe, yes, that is, you're dealing with carbon. So we'd be misidentifying this. So I'll give you some little cheats, some ways to remember which number is which. On some periodic tables, the big number's on the top. Sometimes it's on the bottom, like on this. And so you can't just memorize, oh, the atomic number is always the little number at the top, because it's not set that way. It's not always that, like there's no set way that it has to be. All right, so protons are permanent. Protons, permanent. Try to keep that together because it's a super important idea. If you change the number of protons, you have now changed the element that you're dealing with. Okay, so changing protons changes your element. Now the mass number is the number of protons plus the number of neutrons. So basically this is like counting up all the subatomic particles in the nucleus, because you're counting protons and neutrons, and you guys just told me those are the 2 parts that make up the nucleus. Right? So here it's showing hydrogen. This time it has the mass number, the big number at the top, and it has the atomic number at the bottom. Okay? So again, you can't just memorize, oh, the atomic number is the one at the top, mass is at the bottom, because it might be switched if you look at a different periodic table. Okay? All right, here's how you keep them different, because you have an atomic number and you have a mass number. I get it, it's easy to confuse them. Here's how I remember it. Atomic number is the smaller of the 2 numbers, always. So that means the mass number is going to be the big number. Like, oh, how does that help me remember it? Well, think how small the atom is. The atom is teensy, teensy, tiny. So it's small, just like its number is small. That's how I remember it. Again, if you try to memorize this stuff, it doesn't stick with you very well. You're like, oh man, I'm a good memorizer. You might be, and maybe it will work, but it helps if you just think about it more logically and more with common sense. Like, okay, the atom is small, the atomic number is small. That kind of goes together. And then the word mass is in the word massive. So the mass number is going to be your big one. It's the massive number, at least compared to the atomic number. Little number, big number, small like the atom, massive like the word mass. Then the logic part kicks in. the atomic number only includes protons. It's counting the number of protons. So you're only including one subatomic particle. Well, the mass number is counting two parts, protons and neutrons. So logically, common sense tells us if you're including two things, it's going to be bigger than counting just one thing. So if I count only people with blonde hair in this room, that's going to be a smaller number, probably, than if I count people with blonde hair and brown hair. Counting just blonde haired people, counting blonde haired and brown haired people. Sorry, redheads. I guess we need a third category. Sorry, I have 3 redheaded nephews, so, like,
Why don't you all the way down? It's blonde, brown, and red.
there you go. All right, so again, try not to memorize. Think logically. Atom is small, it's counting one thing, it's going to be the small number. Counting two things, protons and neutrons, it's massive, just like the mass number, it's going to be the big one, right? So between those two numbers on each tile, that's how you can distinguish, because sometimes the 1 will be on top, sometimes the 2 will be on top, it just depends. On our periodic table, the small number is on the top. All right, so the atomic number is on the top. Okay, so there is no number for neutrons on the periodic table. But that's our third subatomic particle, and there's going to be times when we need to know the number of neutrons. So we have to have a way to do this, and it's pretty simple. We know atoms of the same element have to have the same number of protons, or else they're not the same element. But they are allowed to have different number of electrons, and they can form something called ions. They can also have a different number of neutrons and form something that we call isotopes. And we're going to get into those two things later on, but ions and isotopes are versions of an element. It's still the same element because it has the same number of protons, because remember, protons are permanent. It's like the fingerprint, so it has to stay permanent, or else you change what you're dealing with. But if we change the number of the number of electrons, or we change the number of neutrons, we need to be able to figure out how do we get that new number. All right, so again, changing the number of neutrons gives us a version of the element called the isotope. And just because like you're gonna start seeing this, I tell you this now, isotopes, we can have versions of carbon. So carbon-12 is the normal version. We can have an isotope of carbon called carbon-14. And so carbon-14 actually has 2 more neutrons than our normal carbon-12, right? The reason that this is how we name it, we just say carbon and then the mass number. If we just say carbon, you might not know if we're talking about normal carbon or the isotope of carbon. So there has to be a way to distinguish it. But for us right now, we need to determine the number of neutrons, and the way you do that is to take the mass number minus the atomic number. Because if you think about it, it's taking the mass number, which is protons and neutrons, and you're subtracting that from just protons. And so what you're left with is neutrons. And so the way this looks is take your mass number, which is protons and neutrons, minus your protons, which was just your atomic number, and that leaves you with your neutrons. That's the only way to figure out, unless you have the name. Well, no, still. This is the best and easiest way. If you look at your periodic table, I actually have that in the bottom left in my handwriting in like a little cloud bubble. I have that written down for you. All right, so if you see that in the bottom left corner of your periodic table, you'll see this exact thing. Mass number minus atomic number equals your number of neutrons. Okay? All right, so let's take a look at this. So helium 4, carbon 12, carbon 14, and oxygen 16. So look at your periodic table. go ahead and get that out. Oh man. And again, this is super important. Certainly after we color it and coat it, you do not want to lose it. Alright, so the atomic number is your number of protons, right? You might want to put like a capital P at the top. Number of protons and total number of electrons. And then we're gonna try to figure out the number of neutrons, and we're gonna figure out the mass number. So, look at helium. Helium is He. It is in the top right-hand corner. I know that these are small. I'm getting old, my eyes are getting bad. It's making me crazy because I can't see. Like, even compared to like a few months ago, I'm like, oh. Like, I had perfect vision my whole life, and it's making me nuts because like, it's just weird not being able to see like I'm used to. Making me a little crazy, but I get that these are small. The reason I use this periodic table, this is the one that the state of Ohio uses for like when there used to be a physical science test. I don't know if they even still provide this. Last I checked, they still give you this for the biology test. So this is why I use this one. There's other periodic tables where like they're a little bit bigger, maybe a little easier to read. But this is the one that I think is more authentic to what you might see later on. Like, so that's why I use this one. So anyways, you can find helium. Look at the two numbers. What do you see? What are the two numbers on helium's little tile? Give me one of the numbers that you see. Dane?
2.
Okay, he sees a 2. And what else do you see? What's the other number? Hear somebody whisper it.
4.
4. Now, you will see that the mass number is a decimal. We can round that to a whole number, okay? That is, yeah, rounding it to the whole number is fine for us. So you see 4.00, 4 is fine, and 2 is fine. So the mass number is always gonna be the big number. So that's where this 4 came from. The atomic number is always gonna be the small number. That's where that came from. Well, you have to recognize that the atomic number is the number of protons, so that's where that 2 came from. And then we said you have to take your mass number and subtract it from your atomic number, and that's where your number of neutrons comes from. All right, so now let's look together at carbon 12. Okay, so carbon 12, let's find that. It's the capital C is the atomic symbol for carbon. So find carbon, it's kind of in the right-hand side, closer to the top. Billy, what is the small number that goes with carbon?
6.
Okay, so that is the atomic number. So if you have an atomic number of 6, how many protons do you have?
12. 6.
I like 6, because 6, atomic number and proton number are the same. So if you know the atomic number, you automatically know how many protons. If it's neutral, you also know that that's equal to total electrons. All right. I think I skipped to mass number. I can't remember. What's the big number that you see for carbon? Brookston?
12.
Okay, so we'll just round to 12, that's fine.
Yeah.
So if we go to 12, that's our mass number. How do I get the number of neutrons? Gilbert? How about 12 minus? 12 minus 6. You take your mass number, which is protons and neutrons, subtract it from your atomic number, which is just protons, and that leaves you with your number of neutrons, which would be 6. Now, we said earlier on the a couple slides ago that the isotope is named with the mass number following it. So we have carbon 14. So this means that the mass number is gonna be 14. Oh, alright, it should be 14. It's still carbon, so it's still 6 for the atomic number. It's still 6 for the number of protons. And then we know that the mass number is gonna be 14 because it's named that. Otherwise, we would look at the chart and we would see that it's 12, right? The only way I know that I'm dealing with the isotope is if it's named. So there's no other carbon on the periodic table. There isn't gonna be a special one for each isotope of carbon. Carbon is carbon because it's 6 protons, right? And then how do we find the number of neutrons? Veronica?
The mass number minus the atomic number.
Very nice. So we end up with 8. And so everything, you can see the number of neutrons is what is different here. You've gotten 2 more neutrons for carbon 14. All right, so look at oxygen, capital O. Echo, what do you see? What is the small number for oxygen? An 8. Perfect. So how many protons is it gonna have then? Brady?
8.
Very nice.
At least. I want 4.
And then how many total electrons too? Oh, looks like I'm out.
Oh.
If it's neutral, this is a neutral oxygen. Veronica?
8.
It'd be 8. Right? Wait, don't fill it. No, hold on. For total electrons. So if you have a neutral atom, however many protons you have, that's how many electrons you would also have. Okay. All right. What is the big number? What do you see there, Connor? Howard?
16.
Okay, he saw the big number was 16. And so how many neutrons are we gonna have, Dane?
8.
Okay. Okay. Kind of getting the hang of it a little? Okay. Let's go, get logged in quickly. We're gonna start practicing with the Kahoot.
Oh, looks like it's done. I'll be done